Well, good afternoon, everybody. Thanks for coming here today for this presentation. We are going to talk about water quality. And Dr. Fontanier and I are basically going to split up this presentation today, where I'm going to start out just giving some background information, a little bit of the science behind water quality, some of the different parameters we're going to look at, what they mean, what some of the numbers and ranges are. And then Dr. Fontanier is going to take over, and he's going to go through some real-world examples and kind of say, okay, we're going to look at some water quality reports. Now, what do all these numbers mean? And then, even better than that, what can we do about them as turf managers to make our fields better and make our turf healthy? So the first thing is just to think about, where does our water come from? And so, several different folks in the audience have different facilities, different types of facilities maybe, and perhaps different water sources. And so if we think about, globally, like this slide's talking about, there's a lot of things to think about for water, where it comes from, what we do with it as humans, and how we deal with it as humans. And then, you may get your water source for your actual facility, for your turf grass, from a municipal facility. So that water would be coming in from, it could be from a lake or from a river, stream, things like that. It would be treated up to a sufficient level, actually treated to a high level where it's probably good for drinking water, but then maybe comes into your facility through a city tap or a city line or something like that. So in those cases, usually the water quality, so to speak, is going to be pretty good because that water has been treated to a level sufficient for human use, or so we call that potable water. Now, there's other facilities that may get treated water, but it's treated a little bit differently. This is water maybe that's used already and goes through a municipal water treatment facility, so like a sewer treatment, water treatment plant, is treated to a level where it can be released back into the environment, but sometimes facilities can reuse this water and use it for turf grass or plant irrigation at their facility. So you'll see a lot of signs like these, and you'll see purple signage and purple pipe, so maybe we have reclaimed water. Now, in these instances, we can have some water quality issues that we want to look out for and pay attention to with certain levels of certain parameters, like maybe salts or certain nutrients that might be in that water. Even after it's treated to a level sufficient to release to the environment, there still might be some things we need to watch out for at our facility for turf growth. So here's an example of a facility that actually directly pulls water out of a large impoundment or a pond or a lake. And so that's another. So there's no direct treatment first. You're pulling it right out of the lake, but there is treatment, so to speak, in that perhaps through that's water coming in through rainfall, or it could be coming in some cases into an impoundment through runoff and things like that. There's other impoundments where runoff is on purpose. They build it so that runoff cannot enter into the impoundment. So it just depends, and we have to look at all these things, all these factors. And here's another example. So this would be groundwater. So this is pipe underground and a pump to pull water up from underground. And so here again, this could be drinking water quality type, or it could be something that has a lot of salt issues or other things that we really have to pay attention to. And a lot of this just depends on what is the aquifer you're pulling that water from. So all these issues come into play. Some of you may have groundwater, some of you may have municipal, some of you may have reclaimed. Regardless, there are some issues we need to think about when it comes to water quality. So globally, you'll see these statistics like this. Most of the water we have is seawater, with the average total soluble salts are pretty high up there, right? So about 2.5% of the water that we have available globally is freshwater reserves, and about 1.7% of total global water supply would be from groundwater. So there's a lot of water in the world, and just some of it is useful for us for irrigation. Just recently, last year, the USGS put out their latest report for water use across the United States, and as you might expect, total withdrawals for irrigation purposes are the highest, the farther you get into western United States. So those are usually more arid, so places like Arizona, California, Idaho, are going to use a little bit more water for irrigation than maybe places farther east would. But what's interesting about overall water use in the United States, it's actually decreased in the past decade. And so it seems like we overall are doing a good job in the United States of managing water as a resource. We're actually using less over time. But if you were to drill down into just the irrigation part of that, that is going up. And especially in certain places of the country, it's going up over time. But overall, all the water that we use has actually decreased 9% since 2010. So that's just a little bit of background. But really what we want to talk about today is for how do we understand some of these specific irrigation water quality parameters? What are some of the measurements we want to look for? If we get a report, what do we look for? And then once we know what we're looking at on a report, what are some best management practices we can do to help us deal with maybe any potential water quality problems or soil problems that might be affected from the water source. So I'm going to, there's a lot to go through and a lot to cover, and I'm going to go through a little bit quickly and let Dr. Fontanier really get to the good part where we get to the application part. And so there's lots of things that you'll see on a report. And just, for example, here's a list of maybe some soluble salt ions in irrigation water reports that you may see. So you see calcium, magnesium, sodium, potassium, and cations. And bicarbonate, carbonate, chloride, sulfate, nitrate, and boron as anions. So what we'll do is kind of break down some of these individually, some of them together as they interact with each other, and then kind of go through from there. So some general water quality parameters that we'll start out with first, this group here, pH, hardness, alkalinity, bicarbonate, and carbonate. So probably all terms that you are familiar with, at least somewhat familiar with, or at least you've heard of before. So the first one is pH. And pH is a measurement of the dissolved hydronium ions in a solution, or basically a measure of water acidity or alkalinity. Another word for that you'll see is basicity or basic. So we have a neutral pH at 7, and then in pHs that are higher than 7 would be considered basic, and pHs less than 7 would be considered acidic. So most irrigation water that we deal with, samples that you'll have, probably going to be somewhere between 6.5 and 8.5 pH, somewhere in that range, for the most part. So of course, you can find some that are lower, and you can find some that are higher in pH, but for the most part, they're going to be somewhere in there. So pH itself is not a direct problem for water quality issues, but it's an indirect problem. So a high pH could create some problems for us, and a low pH or acidic could create some problems for us. So with high pH, you might get liming or sealing issues going on, and with a low pH, it can be corrosive on metal irrigation components, things like that. But also the pH of the water can affect the pH of the soil, and then the pH of the soil can affect the availability of plant nutrients. So this is a common chart that we see a lot, and this is just looking at different plant elements and pH. So you see listed here nitrogen, phosphorus, potassium, sulfur, and so on. And then you see the pH ranges from 4 to 10 in this particular chart. And then they have some categories from strongly acidic to strongly alkaline or basic there. So you see here in the middle, a pH of 7 for the most part. All those nutrients are pretty readily available. As pH decreases, some of those nutrients, the line gets a little skinnier there, so they're less available at those lower pHs, while others become more available at the low pH. And on the same side, with the high pH, some become less available as the lines get skinnier, and some become more available as the pH increases. What we see a lot with plants is maybe something like iron. As the pH increases, the iron gets tied up and it becomes less available for the plant. So maybe we see some iron chlorosis issues with ornamental plant materials, or even in turf grasses as the pH raises in the soil. And even though I did not list any other metals in here, but you have things like aluminum is a big issue. I know we come from Oklahoma, so in Oklahoma a lot of our soils have aluminum in them, and a lot of our soils can have acidic pHs, and so we get a lot of issues with aluminum toxicity because even though it's not listed here, as the pH would decrease, that aluminum becomes more available, and thus for plant uptake, and then we have some toxicity issues there. Okay, so the next one that I had listed was hardness. And you've probably heard of this before when we're talking about hard water and really the ability to make soapy suds with the water that you might have. So it's related mostly to calcium and magnesium, but also iron, manganese, aluminum, and zinc can contribute to hardness. Can lead to scaling in pipes, typically reported in parts per million, but also milligrams per liter. And just remember, 1 milligram per liter equals 1 part per million. Also with this one, sometimes you'll hear grains per gallon when they're talking about hardness, or maybe you have a water report. And so basically, if you had 17 milligrams per liter of a hardness level, that would be 1 grain per gallon. So if you were trying to categorize that, do I have hard water, do I have not have hard water? Here are the categories. So you'll see something like this. Remember, milligrams per liter and part per million. 1 equals 1 there. So soft water would be less than 50, moderate up to 150, and so on. So if we were, again, you'll sometimes hear that grains per gallon talked about a lot. So that's probably going to be somewhere in that 7, 8, 9 range is going to be hard water for grains per gallon. Or 150 to 300 milligrams per liter. So just basically dividing these numbers by 17 would give you the grains per gallon for that. So is this important for irrigation water? Well, not directly. But some of these parameters that are used to calculate hardness are important. But hardness itself is not necessarily an important parameter we directly look at for irrigation. But good to know about. And you're probably going to see it on a water report. Okay, alkalinity. That's another term that we need to be aware of. So this one is a measurement of acid neutralizing potential. You're probably going to see this on a water report as well. And it takes into account bicarbonate, or HCO3, and carbonate, or CO3, and hydroxide, or OH. So it's going to be expressed in calcium carbonate equivalent, typically going to range from 20 to 300 milligrams per liter. And again, maybe something that we are going to see a lot on an irrigation test, probably more useful if we were taking care of a greenhouse or a nursery, and we need to, if we had a high alkaline water and also a high pH water, and maybe we need to acidify that water, then we'd have to pay attention to that. But for the most part, for turf grass use, this is not, again, a directly important factor, something that's going to be on a water quality test. It's something we can be aware of. But probably we just want to pay attention to the actual bicarbonates and carbonates in the water. And there's something that we can look at called a residual sodium carbonate that we'll talk about here in a minute. But before we get there, so you have bicarbonates and carbonates. If bicarbonates are greater than 120, carbonates are greater than 15, and sodium is greater than 100, all in milligrams per liter, there's a potential for it to create sodic soil conditions. And sodic soil conditions would be something that would be bad for turf and turf growth, and we'll discuss that a little bit later. But essentially, high concentration of these, along with high calcium and magnesium, can lead to deposits of calcium or lime. And typically, when you have a higher pH water, it often contains higher bicarbonates or carbonates. And so they're often listed on the water quality report separately. And so now that we kind of quickly gone through that, and we're just kind of, we talked about hardness, talked about alkalinity. Those are related to bicarbonates and carbonates, so let's just look at those individually. and we can look at something called the residual sodium carbonate. So again, alkalinity hardness not extremely useful for turf irrigation, but instead maybe we see the RSC reported, or we can calculate or use the RSC for turf growth. So what is that? Well, the residual sodium carbonate is right there. You have your carbonates plus your bicarbonates minus your calcium plus magnesium. So basically what we're doing is, instead of looking at them separately, looking at them in relation to calcium and magnesium in the water. And this is going to be expressed in a new unit here that we haven't heard about yet, called milliequivalents per liter. And that's basically a measure of chemical equivalency so that we can directly compare these two versus these two. So in practical terms, we can think about it kind of like football and blocking, offense versus defense. So if your sodium level is greater than 100 milligrams per liter, residual sodium carbonate becomes pretty important. So you can be calculated by looking at carbonates, bicarbonates versus calcium and magnesium. And if that number is 0 or a negative number, that's a good thing for turf growth. There would be no hazard, really. The calcium and magnesium will not precipitate, so they remain available to kind of block sodium. So sodium or sodic soil conditions would be a bad thing, and calcium and magnesium can help us to fight that, basically. So if you have a number less than 1.25, you're doing pretty well. As it gets up higher, now we have most of the calcium and magnesium is tied up, leaving the sodium to accumulate, so we don't have any more blocking. So why is that a bad thing? Well, let's look at sodium for a second here. So high sodium in water is generally considered a bad thing because it can lead to sodic or saline and sodic soil conditions. So this relationship that we have with bicarbonates, carbonates, calcium, magnesium, and now sodium are pretty important. So calcium is a primary ion for soil stabilization, and magnesium is important for secondary soil stabilization. So if sodium builds up in the soil, it can displace those two, calcium and magnesium, from soil particles, basically take their place. And when sodium builds up on soil particles, that's bad for soils. It destroys soil structure, or something called deflocculation. So if there's excessive buildup of sodium in the soil, why is that a bad thing? Well, it destroys the soil structure, and so we get a lot of puddling. The water really doesn't percolate or infiltrate through the soil. You'll see standing water, puddles. You can have wet roots or root rot, low oxygen in the soil profile. So basically you're going to generally have turf decline and possible turf death in these areas. So assessment and management must be based on, not just looking at water quality, but also soil issues as well. So we want to measure the sodium and all these parameters in the soil. And we have to monitor water quality and the soil profile and determine what we're going to do if this site is good for turf use or not. And so basically sodic soils or this excess sodium that can build up in relation to calcium and magnesium is very difficult to manage. Okay, and like I said, I'm sorry I'm going through this really quickly, but we're going to get to some practical applications here. So sodium absorption ratio is generally used to assess sodium status in soils, but also you'll see this reported on a water quality report as well. So they'll measure it as far as the irrigation water is concerned. And so there you see the sodium absorption ratio, abbreviated as SAR. We calculated right there. So the sodium, calcium, and magnesium are in that milliequivalents per liter unit. And to make it even better or easier for you, there's an adjusted version of that, which you may have to use depending on the conditions. But this adjustment takes into account those bicarbonates and carbonates that may be in the irrigation water. So, for instance, what we've done to try to clear some of this up is either report this directly on our water quality reports that we would give out through our university, or just have a little, like on our website, we have a little calculator where you can plug in your SAR units so that you would have your actual SAR value and your adjusted SAR value, and you would use the larger of the two for your particular site or for your particular sample. Okay, so moving on to the next thing now, and just looking at salinity. So salinity, saline soil conditions are one of the more common issues that we will deal with in turf grass, that's for sure. The sodic soils are a problem and are an issue, but by far see more issues with just directly with salinity. So this can be confusing too, and that's what's fun about this. You could read textbooks and read articles, and you'll see all these different ways to calculate things, and maybe different names, and they're all important. And sometimes we can confuse ourselves too, because we want to look at salinity. So you might see TSS when someone is talking about salinity for total soluble salts. You might see TDS for total dissolved salts. You might see TS for just total salts. Or you might see EC for electrical conductivity. All of those are referring to a measurement of salinity, total salts either in the water or in the soil. But that TSS in most water quality books is also used to refer to total suspended solids, which is really a physical parameter, not a chemical parameter like we're looking at here. So total suspended solids is, say, if you had soil particles or a dirty water, so to speak, sediment in your water, or if you had algae or something like that, something floating in the water, so to speak, that would be your total suspended solids. Where the salts, we're looking at, like sodium and chloride and things like that. So, what you have to really read carefully, I guess, if you just see TSS or TDS or something else listed there. Now, if you see EC, you know what that's talking about. That's talking about electrical conductivity, and that's a measurement for salts. So EC is relatively easy to measure either in the field or in the lab. You can buy little probes to do that out kind of on-site in the field. Of course, you can do this, send in a sample and do it in the lab as well. Okay, so at least if you see EC, you know you're talking about salts. However, there's no, agreement on which unit should be used for EC. So you may see a water quality report, and you may see from one lab they report EC in a certain unit, and from another lab they report EC in a different unit. So here they are listed here. So they can be reported in DS per M, or decisiemens per meter, millisiemens per centimeter, microsiemens per centimeter. And so basically down at the bottom here is kind of a little, conversion for you. So 1 decisiemen per meter is going to equal 1 millisiemen per centimeter, which equals 1,000 microsiemens per centimeter. So the good thing about all this is that they're recording these and giving you the slides, and so that you can refer back to some of these numbers. Okay, so also for EC, you'll see in some books and other places a couple more units. You might see millimoles per centimeter and micromoles per centimeter listed as well. So 1 millimole per centimeter is equal to 1 decisiemen per meter, and 1 micromole per centimeter is equal to 1,000. 1 millimole per centimeter is equal to 1,000 micromoles per centimeter. So there they all are. 1 decisiemen, 1 millisiemen, 1,000 microsiemen, 1 millimole, 1,000 micromoles. Okay. EC is basically just sticking two probes in the water and the soil sample and measuring the electrical conductivity between those two probes. But it's not a direct measurement of total dissolved salts or total salts in the sample. But EC can be used to estimate or convert those numbers of EC into total salts or total dissolved salts. So the way to do that, and you may see this on the report as well, is if your TDS is reported in milligrams per liter, you can take your EC, 0.64 times EC to get your total dissolved salts. So basically, if you had an EC measurement, you plug it in here, and that EC measurement was in one of these units, you multiply it by 0.64 to get your estimate. And same thing here, if your EC measurements in decisiemens per meter, millimoles per centimeter multiplied by 640. And basically that's just looking at, some of these are 1, some of these are 1,000 depending on the unit. So very similar here. Depends on what you're going to multiply by 0.64 or 640. Okay. And I know this is a little bit confusing, but to make things a little bit easier, so to speak, it does not always fit. And so not all salts have the same electrical conductivity. So you may, even though I've given you 0.64 or 640, you may see other published numbers that, depending on the salts you're talking about, the conversion factor may range from 0.55 or 550 to 0.75 or 750, depending on the situation. But for the most part, what you would typically use is that 0.64 or 640 to get your TDS estimates, or total salt estimates, using an EC value with one of these units. Okay. So to make it a little bit easier, here's a chart that kind of has them both listed. So what if you had a water quality report and total salts in milligram per liter was less than 320? Basically, that'd be excellent irrigation water category. If it was, say, 200 or 100, something like that. If it's between 960, 320 and 960, that would be a little concerned. And as we get up here closer to 2,000 in total salts, 2,000 milligrams per liter, or parts per million, now we have to think about leaching those salts on a regular basis. And if we get up very high, say above 3,000 to 4,000, then it becomes very, very important to pay attention. And anything above, getting it roughly in that 4,000 range is going to be unacceptable. And so here's the equivalent EC values, but notice just have one unit there, the microsiemens per centimeter for that. So there's your EC values that would be associated with that. And again, if I have to pay attention to what unit a table is using, whether total salts in milligrams per liter, EC in microsiemens per centimeter, if that was in decisiemens per meter or micromoles per centimeter, it would make a difference. Okay. So here is, since we talked about salinity and we talked about sodium absorption ratio, here's kind of a nice chart that shows you the relationship between those two parameters. So here you have total salts ranging from 0 to 3,000 milligrams per liter. And then here from 0 to 40, you have your SAR, or sodium absorption ratio. And so why this makes a difference, because you can have a relatively high sodium absorption ratio and a relatively low total salt value, and it could still be a severe issue. Even though the salts aren't very high, that sodium absorption ratio may be very high, and so on. And so when we have a lower sodium absorption ratio but a high salt value, we have a slight problem there. So the way that they work together is maybe not what you would expect when first talking about these or thinking about these. High total salts can help with infiltration at medium to high SARs, and high calcium and magnesium can counterbalance the effects of high sodium. And so another way to look at this is there's a slide set, Crop Science Society of America slide set from Haravande, and he's got the listed here a little bit differently. And so here's how to interpret that sodium hazard. And you have your salinity in EC. And this unit here is decisiemen per meter. And you have your salinity with total dissolved salts in milligrams per liter. And then how does it affect your restriction in use based on SAR value? So here he goes from a level of 0 to 3. And if the EC equals here, SAR 3 to 6, EC here, SAR is 6 to 12. So basically, if you had, say you had a report that your SAR was 3, and your EC was less than 0.3, so we'd be SAR of 3, EC less than 0.3, there'd be a severe restriction in how we want to use that water. So that's basically how you would read that table there. Okay, so in addition to these, the way that they interact and work together, there are specific issues just with sodium itself, or chloride, or boron. And they can cause problems if just that ion or that specific element itself is in excess. And so again, this is from the Crop Science Society slide set with Harboni. So basically, this is what turf will look like if it has excess sodium. And this particular sample is basically just a sodium issue. This sample is a salt issue. And so there you see actually the white crusting on the turf or on the soil itself there. And this issue here, again, is going to be a salt and a bit of a sodic issue, and it's hard to see, but it kind of turns a little bit black on those issues sometimes. And then here you see it on plant materials. This is actually a chloride toxicity issue on some ornamental or some trees, woody trees here. And so you'll start to see that leaf burning, leaf tip burning, things like that. Here's another example of a boron where you get that burning around the edge and the tip of the leaf from just excess boron. So where would we worry about these types of issues? Again, if you have the water source, that you could have these issues from groundwater for sure. But probably for the most part, this is going to be if we're using the reclaimed water from a municipal water system, something like that. You'd have to pay attention. So again, here's another summary, kind of in total. And again, I know I went through these very quickly, but here it is all on one page of pH, desired range, usual range, and so on, and average of a domestic water source, so that'd be like a municipal drinking water source, and average of a reclaimed water source, and so on. And so you see pH, hardness, alkalinity. You see the bicarbonates, the carbonates, the EC, or electrical conductivity, the total dissolved salts, measurements of total salinity there. And then you see the sodium permeability numbers of sodium absorption ratio. I didn't mention what RNA means, but it's basically an adjusted type sodium absorption ratio. It's residual sodium is what the RNA would stand for. Here you see residual sodium carbonate, and then EC again. And this is out of the Duncan, Carroll, and Huck Landscape Water Quality textbook. So just continuing on. So basically, went through all those first slides, but these are the ones that you get a report, and these are the ones that are important to you. You're actually going to refer to and figure out where you are as things stand. So here we see the specific ions of sodium chloride and boron, and the specific impact directly from foliage uptake versus impact from sprinkler irrigation, and then some miscellaneous parameters as well. Okay. Lastly, here are some specific nutrients that may or may not be listed on a report. And so you see nitrogen, phosphorus, potassium, and so on. And maybe what we want to look at here, pay attention to is, are we doing any fertigation or anything like that, or adding fertilizer to our water source as we irrigate? Or are we worried about issues of runoff, nutrient runoff, or things like that? We want to monitor some of these parameters, such as phosphorus, which can be detrimental if too high, and we have off-site runoff of that water, especially into other water bodies, which can cause algal blooms and things like that. Okay, just a few more: copper, zinc, sodium, and chloride listed there. So last thing, just very quickly, before we turn it over to Dr. Fontanier, it's also, even though I haven't talked about it a lot, when we're talking about sodium, sodic soils or saline soils, our soil texture is going to play a big part in that as well. If we need to leach water through the soil and we have larger soil particles, that's going to be relatively easier versus if we have very fine soil particles like with a clay. So it's a good idea to conduct, whenever you're taking a water quality sample, it's just a good idea to always take soil samples or multiple soil samples from different locations on your property as well at the same time. When you take a soil sample, you can get your basic pH, nutrients, organic matter, things like that tested, but also you can ask for a full salinity report or a saturated paste, which may mean you need to use a little bit more soil to do that, but maybe a good idea to do that if you're trying to measure or monitor soil salinity. Okay, so it can be confusing. Hopefully those charts will help you as you get through it. We're about halfway through, so I'm going to turn it over to Dr. Fontanier, and he's going to go through some more practical uses of this information and try to make it a little bit easier to understand.
All right, thank you, Dr. Moss. I think I'm going to try to walk around a little bit. All right, so I like to start with a picture like this and a question. We look at this kind of scenic waterway, a lot of vegetation growing, and you ask yourself, that looks pretty good, right? Is that good? Can we use that water? Maybe, right? How do we know? How can we be sure to test it? So we just got through, that's kind of the reason we're trying to go through this. We really can't know unless we actually test it, and that might mean sending it off to a lab. It might mean that you have a little EC meter on hand and you can test something like the salinity yourself. But we want to test it, right? And if we're going to use a lab, one thing we want to be sure and do is take a good sample, because if we don't have a nice representative sample, it's going to be bad data that we get, right? So this is just one way of doing it. Usually you want to contact your test lab that you're going to use and see what they recommend. But usually something like a 4-ounce clean plastic bottle will do the job. And you want to fill that up as much as you can. And you can get results, maybe within the week from that lab. And so that's pretty good. And you can use a private lab or you can use one of the state testing labs, whatever you prefer. The key is you just make sure you're paying attention to all those parameters that Dr. Moss went through. Make sure the units that they're reporting are what you understand what the units are, so that you can compare it from year to year or to a different table. And so you want that sample to be representative, right? And so the best way to do that is to actually try to get it straight from the sprinkler head itself, right? That's ultimately what's going on the grass. And so that's the best way to do it. And you kind of want to prime that system a little bit. So let the thing run for, say, 10 minutes or so. Just make sure you have a good representation of the water that's coming out of that system. And then you take your sample. All right? And so when we've done that, we send it off. We get a nice little report, and we have to know what the heck to do with it. All right? And so some of the highlights from the parameters that we just went through are the pH, the bicarbonates, the salinity, and then sodium. And really for a lot of folks, when they're talking about poor water quality, the first thing they think about is salinity, and maybe the second thing they think about is sodium. But probably things like pH are the most common, right? Okay. So we'll look at a few examples okay, yeah, there we go. So here's an example of a municipal water source, and you can see it's got a lot of information on it: cations, anions, some pH, EC, all these different parameters, and some of those may or may not be that useful to what you're trying to figure out, but it's a lot of information, and so you can always look at it in detail. But really focusing on some of the ones that are most important. A lot of times you want to start with something like pH, all right? pH. So we're shooting for a 7, right? That's nice and neutral. It's pretty, that would be great. In this case, we're at 7.7, right? So is that okay? What do y'all think? That's pretty good. That's not too far from 7. It's a little bit basic, but certainly something that we can work with. EC, right? And here our units are in micromoles per centimeter, okay? And I'm not going to ask y'all to reach back and remember what the ranges are, but we have a 380, okay? If we look back at our chart, we'll see that that's pretty good too. That's actually very low salinity going on. Remember, this is just a municipal water source, so hopefully we don't have a ton of salts in that to begin with. We look at something like boron, all right, that's pretty marginal. And then bicarbonates, all right, bicarbonates. Typically the value we start thinking about bicarbonates is about that 120, so we're still in pretty good shape, but not something to totally ignore, but we can probably assume that that's not going to be a major challenge for us unless we have a really bad sodium issue. Well, if we look down here, this is the key value we might want to look at, SAR. All right, and so it's not just the sodium, as we talked about, it's the relationship, the ratio of sodium to the other salts that are in there. Because if we have a lot of sodium, it messes with our soils. But if we have enough calcium to counter that, then sometimes it's not as big of a deal. And so in this case, our SAR of 0.8, that's also pretty good. And so pretty good water sample. We could probably use this, and you can see here, the salt and the sodium are low enough that there shouldn't be any problem from use. Okay, so this isn't maybe the most ideal water because our pH is a little high, but it's pretty good. I think most folks would be willing to use this, and we could grow pretty good turf with this sort of water. Here's a second municipal source, and so we'll see this one, see how it compares to that last one. All right, so we'll start again with pH. What do y'all see there? A little higher, a little more basic. We're starting to get into areas where we really probably want to look at some sort of management technique to either, if we're able to treat it at the source, that's great. Otherwise, maybe treat the soil. Try to get that pH down. We start running into issues with that nutrient availability, perhaps. All right. EC, salinity, okay, 476. That's still pretty good. All right, so we're not really in trouble there. And again, this is another municipal source, potable water. We would hope that the EC is not too terrible. And again, boron's fine. Bicarbonates, all right, we were talking about 120 being the starting place where we start to think about bicarbonates, and we're up around 150. So now we've got maybe elevated pH, okay, and that's probably explained in part by having some of these bicarbonates in there. All right, let's take a look at our sodium. Okay, sodium, SAR, our sodium adsorption ratio, that's 1.5. Okay, and so if we go back to our charts, all right, anybody remember what a bad SAR value was? You remember that far back? Yeah. So we start worrying maybe around 3, get up to about 6, it start really getting to be poor. Yeah, so we're still in pretty good shape. All right, so maybe we have a little bit of bicarbonates, maybe just a little bit of sodium, but really nothing to start to worry about other than, again, perhaps a little bit of pH, okay? So this is something where if you're in an area where you do have occasional rainfall, all right, you might just try to go deep and infrequent with your irrigation, rely on Mother Nature to help keep things kind of dilute, keep the pH down if you can. Maybe pay attention to that pH a little bit more and think about modification, particularly if you're going to be using pesticides that are sensitive to pH and using the same source for that. You want to pay attention to that as well. All right. We have a reclaimed water source here, okay? And so if we think about this, this one probably is going to be a little different than those potable, we would hope, right? And so we start with pH, and pH is, again, 7.7, not too bad, a little alkaline, but not too bad. What we noticed, though, is the EC now is about double what it was in that last water sample. So we're getting close to 1,000 there. And really, that's not good, but it's really not that bad for a reclaimed water source. Okay, and so if this was your site, you're going to have a little more salts with a reclaimed water source. But you can kind of watch that value and see how it changes with time, and make decisions based on, okay, it's getting up there a little higher. Maybe it's time to come in and do a deep leaching or a deep flushing. But if we're staying in this value, maybe you feel like, again, I can let Mother Nature help me out, let some rainfall hit, and I may be okay. Bicarbonates, okay, so we're well above 120 there. And so in this case, in my mind, we want to actively manage for that, or at least consider what are my options for resolving the bicarbonate issue. The one saving grace here is going to be that despite having high bicarbonates, we're not too bad in the sodium area, all right, and that has to do with the salinity being a little bit higher, and so we've got some calcium, we've got some magnesium in that system. And so our SAR still isn't hitting that 3 or that 6 value where we might consider it an issue, right? And so here they say water is suitable for most crops under most conditions. There may be an eventual problem if you're on a very heavy soil where you can't get any leaching, or a very arid region where you don't have any help from rainfall. But by and large, you can manage this with monitoring your levels, coming in with maybe a gypsum application periodically, and relying on rainfall to dilute things down. Okay. All right, this is one more reclaimed site. And we can see here pH now is getting up higher. All right, 8.2. So we want to be worried about that. We want to be worried about EC, but again, this one here still isn't that bad, right? Still not that bad. If we keep going, bicarbonates above 120, a little bit down from our previous sample, and something of concern. But really in this example here, what stands out? What stands out to y'all? The SAR. So SAR, right? So yes, pH is a concern. EC is starting to get to be a concern. But really that SAR is what we're worried about. Now we have the potential for that sodium permeability hazard to become an issue. Again, if we have any kind of clay in our soil, it's a potential for accumulation of sodium over time, potential for that loss of infiltration and moisture retention, all those negative properties of a sodic soil. And so this water is generally is sufficiently low quality, all right, that you could consider it a restricted water source. So it's something that if you have the ability to not use, try not to use it, right? It can be used safely on well-drained, permeable soils. And so maybe you can use something like that if you've got sand-based systems or a sand capping or some way to really drive that sodium through the profile. All right. The practice of using excess irrigation to keep the soil leached of salt when rainfall is insufficient. And so they say here, good soil management practice must be used and maintained. And I'd say kind of, when I think about, we always want to use good soil management practices, but here it's now you start talking about a proactive approach to managing your soils. All right, you know you're going to have an issue if you don't do anything, so let's get on top of it from the get-go. If the water is used extensively, this is where monitoring not just the water over time, but that soil over time, and you want to track to see how are things changing. Poor irrigation quality isn't really, a water problem as much as it is a soil problem, right? We saw pictures of some of the ornamentals and trees that can have a lot of foliar salt injury. Most of our turf grasses can handle that. The issue becomes when they get in the soil and they start messing with how that plant functions in the soil or how that soil serves as a resource to the plant. And so it can be a cumulative process. And so we really want to watch it over time, and that's where the soil sampling comes into play. All right, good. That was my next slide. Soil testing, right? So And as Dr. Moss pointed out, you really need to ask for a detailed salinity report. That's the only way to get that useful information for things like soil EC and SAR values. You can certainly get a soil pH from a routine nutrient test, but that only gets you so far, right? If you really need to know salts, if you really need to know sodium, that detailed salinity report is what you want. So the next couple slides are kind of just a quick, maybe they're a little bit intuitive, a little bit obvious, right? But we're going to talk about if you have a water quality report and a soil test report next to each other, how they can be very powerful tools to help understand exactly what's going on in your site. So, believe it or not, water with high salts will lead to a saline soil. All right? So if we have a water report and we've got pretty decent SAR, pretty decent bicarbonates, no boron, but our salts are very poor, okay? That's TDS of 2700. That's pretty up there. And you look, we have a clay loam soil, so a pretty heavy soil. All right? Sure enough, our salinity report from our soil says it is saline. All right? No issues with sodium. The SAR in the soil is okay. That's pretty obvious. That's intuitive, I hope. But time and again, when folks start looking at managing for poor water quality, they mix those two concepts up like they're the same thing, and the same treatment doesn't work necessarily for both. And so I think it's really important to drive home that yeah, this is what we're worried about. We're worried about salts building up in our soil. Okay? How do we deal with that? Well, we have to get them out of there. We need to leach the salts out. That's the only way to get that done. All right.
Dr. Fontanier, sorry.
Yeah.
This is a good example, I think, of paying attention to. So from this soil salinity report that we were given, you'll see TSS up there, and that was total soluble salts. But as I referred to before, a lot of times you see TSS as total suspended solids. But the report we have gave us TSS. So that, and again, that's pretty intuitive because this is a soil salinity report. But just another example of why it's a little confusing sometimes. Thank you.
Thank you, Dr. Moss. So get to know your lab and what they're referencing. Definitely key. Whether it's a soil routine nutrient analysis or any kind of test, you need to understand what the units are and what we're talking about. But so here's an example where sodium's involved. So we have a water quality report. Salinity, it's getting there, but not too bad. When you're above 1,000 TDS, you probably want to think about managing that, but nothing that I would consider critical. The SAR, though, of 7 is fairly poor. That's something where, particularly with a clay soil type, you'd start to worry about the buildup of that over time and the loss of permeability and the loss of ability to get anything to hold moisture and to grow into it. And if you look at the paired soil test, you see their salinity is normal, but the SAR is 16, and that's going to be very problematic. And so now the remedy is going to be different. Yes, you want to leach the sodium, sure, but now we start bringing things like gypsum as a tool to help not only, primarily to flood the system with calcium, all right, so that we can then remove the sodiums a little bit more selectively. All right, so now gypsum becomes a player, whereas when it was straight salinity and there wasn't a sodium problem, the addition of gypsum probably wouldn't have helped very much, right? It's just adding more salinity to it, essentially. If we have both, because quite often we have salts and sodium at the same time, you can see here we have over 2,000 in our TDS value, so very poor. The SAR, 6.6, again, very poor. And it leads to the old saline sodic soil, which actually in some ways isn't as bad as the straight sodic soil, but still a concern. In this case, we might want to use some gypsum in moderation, but we really have to pay attention to what is the salinity of our soil, and can we use as much fresh water periodically to clean that out. And And so this one here, okay, so this is an example now where we have a high residual sodium carbonate mix for a sodic soil. So if we look at our water test, all right, and we see salts, pretty good, 416. SAR, also pretty good, right? But we're going to irrigate over time with this water, and it's going to turn into an SAR of 13. All right, and that's now considered a sodic soil. So what happened? What happened? Well, we have bicarbonates. Bicarbonates, okay? And bicarbonates act by removing calcium from the soil solution. In a sense, it's like you didn't have the calcium in the water to begin with, right? So in a sense, the real SAR, or the effective or the adjusted SAR, is actually poor, okay? So if we account for how bicarbonates behave when they're in the soil, we know that over time, this particular water is going to give us a sodic soil. And so now we have to manage it like a high sodium, high SAR irrigation water source. And so that's going to be, again, your gypsum treatment. In this particular case, you can try to target the bicarbonates themselves through acidifying the water, or you can treat it like a conventional sodic soil. And I'm going to skip boron to move on. So turf management and poor quality water. So you've got the test, you've got your sample. You sent it off to get tested, okay? And you got the report and you figured it out. You know how to interpret it now. And so we need to manage it, all right? So we've gotten this done, right? We've identified our problem. The next step is developing a plan. We need to execute that plan, and probably the most important thing we can do is assess how it worked, right? And how do we do that? Take another test. Yeah. So this is one of the challenges with poor irrigation water quality. It's a cumulative. It's an ongoing thing. It's something that changes all the time, and so actively monitoring to see how your management is affecting the soil and plant health is always an important part of this process. If you're lucky and you get to pick the grass you're going to use, you want to make sure and try to pick, this is kind of Turf 101 for every kind of stressful situation, is pick a grass that's going to be adapted to what you're trying to look at. So if you can pick a grass that's more tolerant, well that's a good way to go. It gets you a fighting chance. In the warm season world, Seashore Paspalum certainly fits that mold. And most of our warm season grasses are at least moderately tolerant to salinity. But certainly you want to try to determine what grasses grow well in my climate, and then can I pick the most salt tolerant grass available if that is indeed the issue I'm facing, right? That's always a good starting way to go. Another thing you want to look at is, because this is ultimately coming from your irrigation system, okay, is making sure your irrigation system in general is efficient. All right, maybe you're using very sound irrigation management practices, you're following weather station ET, you're applying a leaching fraction, you're doing all kinds of good things. Well, you want to make sure you're doing all that as uniformly as possible, because if you're applying essentially poor irrigation water quality, you're also applying salt, right? And so if this area here's getting less than this area here, you might see salt buildup here, or maybe that's getting enough to leach potentially right here. And this area here is just getting enough to kind of use up, and then the salts get left behind. And so you're going to have lack of uniformity there because you're not able to irrigate efficiently. All right, and I mentioned leaching fraction. And leaching fraction, so there's a couple ways to leach salts, right? One is to just dump a bunch of water on it one time and try to flush it out. That can be challenging with most natural soils. It's hard to put that kind of water at one time without it just running off, right? So rather than do that, we can try to adjust our normal irrigation cycle to use a leaching fraction. And that's essentially overwatering a little bit on each cycle. so that we're pushing water below the root zone, and that's going to carry with it some of that excess salinity that builds up over time. All right? How do we do that? Well, there's a little formula you can find here, and essentially it says, based on the salinity of your water and based on the salt tolerance of your grass or your plant, you can estimate how much you need to overwater to maintain the same sort of conditions. Okay? And so this ECW is the irrigation water salinity in decisiemens per meter right here. All right, and then you have that value here again, and then this value here, this EC threshold is you can find that from a chart. Typically, a lot of the textbooks or online resources, you can find a chart for your particular grass species. And so the value of 6 is commonly given for a lot of our moderately tolerant turf grasses. And let's say they had a irrigation water quality of 2 decisiemens per meter. Okay? And so you just plug those numbers in, 2 decisiemens per meter here. Here's your turf grass salt tolerance threshold of 6. And there's your soil salinity or your water salinity again. And so they'd come up with this value, and that would mean that you would need about 7% more water just to help flush things out. Okay? So this is a normal recommendation. Again, when you aren't able to just leach the system all at once, is to do it over time with a leaching fraction. So you can calculate it this way, and it's a good way to account for it as well. So here's an example of folks using it in a research setting. This was done in Southern California. And you see, here's their water, okay? They had 2 water sources. They had their good water source and their bad water source. And so the bad one had an EC of 4.4 decisiemens per meter, and it had a total salts of almost 3,000 parts per million. And so when you look at their different irrigation amounts, so we went from 80 to 140% of ET, okay? The good water resulted in a soil EC of about 1.5 for all of them, right? No differences. When we use the bad water over here, okay, you see the lower irrigation amounts had much higher salinity in the soil. This very high, the 140, had actually got a significantly lower salinity value in the soil, right? So what's happening there is they're irrigating at a slightly higher amount. It's driving salts over time out of that root zone. And so it's maintaining a little bit more tolerable environment for the plant roots. And so what you see also is better quality turf at that higher amount. And so this also kind of points to the fact that salinity is, in a lot of ways, acts as a sort of drought stress as well. They behave similarly. Okay? All right. Let's check on time. So we also have a lot of products out there on the market for sodium or for salinity. And, sometimes it's confusing to figure out what you really need. And I'm not going to talk about any specific products. But, as a generalization, things that help with salinity or drought stress are going to help with salinity stress. And so, using things like wetting agents to ensure you have uniform, the irrigation supply is going to be uniform in the soil can be very positive. It can also help with moving water through a profile when we're trying to leach. And so those are things that just in general are positives for poor quality water management. In general, sodium, we want to apply a calcium product. Most often that's going to be gypsum. And part of the reason it's gypsum is because gypsum isn't going to raise our pH, and it's very soluble, so we can put it out there nice, and it's easy to get a hold of. So bicarbonates, we're really looking more at sulfur or some way to acidify that system. We're trying to drive out those carbonates out of the water if we can, or if they're causing pH issues, then we're trying to tackle it in the soil with say, an elemental sulfur application. So, do calcium-based products work at removing sodium? Well, there's probably a lot of research out there that shows this. Here's an example of one where the untreated, and this is sodium content in the leaf, and so you can assume that the sodium content in the leaf is going to be related to the sodium content in the soil, right? And so, untreated, over 1,300, we put a 10-pound rate of gypsum out, really no change, okay? But the much higher rate, marked improvement there in terms of reducing sodium in the system. What does that mean? Right. But does it mean we should use 40 every time? 40 pounds? It means that in this particular case, we would want to look at if we put 10 pounds out and weren't getting the results we wanted, okay? Maybe it means that our sodium issue is so significant we need to put a little bit more out there, right? So, you can play around with some of these rates on these gypsum products to kind of fit your needs. So in this case, they had a sand-based system, but it was building up sodium and causing issues, and that 10-pound rate just wasn't really doing anything. So the other thing is this is just a single application, right? If you're going to do a 10-pound application, okay, that might be something you might do periodically over time. That's a lighter rate, okay? Anyway, so that's part of the kind of the reassess how things go. So here's an example of several products, and this is soil EC. After various products, most of them contain gypsum. All right, and what we see here is that this value here are all higher in salinity. Which ones are those? We look at it's gypsum. I don't recall what this one was here, but here's another one that has gypsum in it. So we have products that have gypsum in it, raising our salinity. Well, how'd that happen? Gypsum's a salt, so we have a salinity problem. Maybe gypsum's not the best answer. If we have a sodium problem, okay, now we're looking at gypsum as an option, right? So if it's straight salinity, keep in mind, if you're adding gypsum, you're adding salt. So you want to be cautious there and paying attention to that. What about pH? All right. All right. If we look here, the gypsum product, right here, it's lowering pH, and so that's one of the reasons we want to consider using a gypsum product if we have a sodium problem. It's going to help drive that sodium out. All right, and then as a result, we're going to have some improvement potentially in our pH as well as our SAR. Okay. So key points there: calcium and gypsum-containing products will help with sodium problems, not always with a salinity problem. And if you have high pH caused by sodium, then those products can sometimes help with that as well. Aerification. All right, so aerification to me is one of the cornerstones of salinity management or any kind of poor water quality issue. Absolutely critical in my mind. And depending on your situation, you don't necessarily have to get too complicated, right? Even a simple spoon type or airway style can be effective on, say, a native soil where you're going to get some rainfall to occur, right? And you're just trying to create opportunities for water to get in and dilute that poor irrigation water quality, right? So can we use something that's easy just to open things up a little and get a little more moisture in? Absolutely, right? But certainly, having a very strong aerification program is beneficial to the plant in a lot of ways. In this case, it's going to help get moisture in. It's also going to give you a chance to come in with things like your gypsum applications and get them incorporated in the soil a little better. And so, a lot of folks like to time those applications with airification, and it makes a lot of sense to me. Again, here's just an example. This was even on a sand-based system, right? You wouldn't think that airification would have that as big of an impact, but here we see, using an airification tool, this was the shockwave versus not. Okay, the SAR dramatically decreased in that sand root zone because we airified, right? And when you look at a picture like this, it starts to make sense, right? You say, oh, okay, that makes sense, because even in our sand-based systems, we've got the potential for organic matter and various layers to occur that can help hold on to salts, that can impede water movement. And so maintaining a good channel with the surface so that we can push water through is a good thing, okay? If possible, sand capping is always a good management tool. If you're looking at really poor quality water, you need to be able to drive those salts out. All right. So internal drainage, if you can do sand capping, that's always a good thing. If you can't build it on the front end, sometimes you can come in after the fact and build those with top dressing programs. So come in with internal drainage, put in several applications of heavy top dressing, and build something where you can now feel comfortable that you can move some of those salts off-site, out of the root zone. We talked about not adding gypsum if you've got a heavy salinity problem, but really any of our fertilizers, most of them are all salts also. So trying to use a low salt index fertilizer is a good practice. Just any little bit helps, right? So if we're using high salt index fertilizers, and we've got salty irrigation water, we're compounding the problem potentially. And then sometimes, blending water sources can be a key. And so you've got access maybe to one water source, and you have unlimited access to this terrible water source, right? Maybe that's what a deal, right? On the other hand, you have a restricted quantity of really nice quality water available to you, and so if you can blend that, or you can find a system that really works for you, and try to target a value. So here's an example where they had an EC of 7.5, 7.6 in this shallow aquifer. So that was going to be tough, right? It's going to be hard to grow, and this was in Vegas, so they're not getting rain, and that's what they're going to be putting on. But they had a water source here that was much better. And they figured that, if we can just figure out how to blend these two and get to 6, we think we can grow Bermuda grass. And so that's what they did, and it worked out for them, right? So, trying to be creative with some of the water resources that are available to you. You certainly want to keep your eyes open and think things through. Okay, so just kind of summarize some of these things. We want to irrigate with a leaching fraction, or perform some sort of periodic flushing if we can for salts. If we have sodium in our soils, gypsum becomes our answer. If we have a calcareous soil, we can instead use elemental sulfur, and that sulfur plus calcium makes gypsum, and it works out for you the same. If we have a heavy bicarbonate load in our water, that's where acid injection or some sort of modification of that water source might be important. Airification and top dressing, 100%. We want to keep that as part of our, not just our normal agronomic management plan, but part of our irrigation water quality management plan. If we can include subsurface drainage or sand capping, if we don't have that, that's sometimes a must for long-term success. And then if you can, try to dilute bad water with good water. In some cases, that can be a pretty good option. All right, so we also have some issues with recycled water, special areas of concern. We've got human health and safety. Obviously, it's a different kind of water. A lot of times these issues are regulatory, but they're also perception-based. So you guys just need to be aware of that. But really what I want to talk about is quality of water and quantity of water. We talked about the quality of water, right? All the things you want to look for in terms of salinity and sodium and maybe boron. But we also want to think about quantity and availability. Sometimes, those reclaimed water sources are, they're not provided to you at the times that you want them, or maybe they're provided to you in times you don't need them. And so having a way to store that water if you need it. When you ask for a certain amount of water, did you factor in the amount of leaching fraction that you needed? If you're getting a water, like I said, it's an unrestricted water source, but it's got high salts, or what have you, you'll make sure you're thinking about how much you need to be able to leach those salts as well. And then, like I said, how do you deal with any excess water that comes out? So those are all questions that you want to be thinking about when you're looking at some sort of reclaimed water contract. All right, to conclude, can we grow grass with less than ideal quality water and be successful? Absolutely. But we want to periodically sample and test our irrigation water. All right, and so that might mean if you're in really using reclaimed water, or you have a shallow aquifer that might be highly variable, that might mean seasonally. So multiple times a year testing and looking at, see how things change. If we can, pick turf grasses that are salt and drought resistant. Okay, and so that might mean looking at some of the latest cultivars that are out there and looking at things like NTEP or other resources to identify really good quality cultivars. Understand that there are limits to what you can do when you have poor quality water. So know what those limitations are and how to manage them, and then ultimately apply the appropriate management techniques to prevent that kind of accumulation issue, that soil issue over time.